Hello everyone, my name is Sasigala. My student ID is W1947920. This video presents my coursework for Applied AI 2026. My project is an AI powered email spam detection system under the domain of cybersecurity and communication. The main goal is to build a machine learning model that can automatically classify emails as either spam, unwanted, suspicious, or harmful emails, or not spam, also known as ham, legitimate emails. In this presentation, I'll explain the application area, a comparison of AI techniques, my prototype implementation using multi-nominal naive Bayes, and then I'll discuss testing, evaluation, EDI, and sustainability. So let's go to part A. There's a little application area review. Email is one of the most common communication tools used globally by individuals, businesses, universities, and governments. But along with email usage, spam has also increased massively. Spam emails are not only annoying; they are also serious cybersecurity threats. Many spam emails contain phishing links to steal passwords or bank details, malicious attachments such as malware or ransomware, fraud offers like fake prize loans and investment scams because of billions of emails are exchanged daily. Manual filtering is not realistic. Early spam filters used rule based systems, meaning keywords rules like free money or click here. However, spammers quickly learned how to bypass these rules by changing spellings, using random words, or just hiding the links. That is why artificial intelligence became important. AI based spam filters can learn from historical email examples and detect complex patterns beyond simple keywords. Um, well, how is AI applied here uh, in this AI spam detection? It mainly done using machine learning and natural language processing, also known as NLP. The workflow usually looks like this. First of all, we collect labeled email data, spam or ham, process the text, um, and convert the text into numeric features like bag of words, TF-IDF embeddings in advanced systems. Number four, we train a classifier and evaluate it. Use the model to predict spam on new emails. Also, in real systems, spam detection can include metadata such as sender IP, sending frequency, or domain reputation. But in my prototype, I focus mainly on text based classification, which is a standard approach for this coursework. Well, we can talk about literature, a review summary. Next, I reviewed key research studies. Dada et al. 2019 reviewed many classical machine learning algorithms and found naive Bayes performs strongly for text spam filtering, mainly because it is fast and effective. And there were a few others, like Sahami et al. 1998 was one of the early works of proving probabilistic learning can beat rule-based filters. More modern work, like Singh et al. 2023, shows deep learning models such as CNNs and LSTMs can capture deeper semantic patterns and reduce errors caused by spelling tricks. Eldemore highlights that phishing detection improves when we combine text with sender identity and behavioral features. So, overall research has shown that spam detection has evolved from classical machine learning to deep learning, and obviously a few hybrid approaches. But for a strong prototype baseline, naive Bayes remains highly competitive. Um, com- but we can see how we compared these three AI techniques in part B. Um, Multi-nominal naive Bayes. Naive Bayes is based on one of the most commonly used theorems. It assumes words are independent, which is not fully true in language, but surprisingly, it works well for spam detection. It learns which words are common in spam, which words are common in ham. Now the strengths of these is that it's very fast training and that has good prediction. It works well on small to medium data sets. Very easy to interpret compared to deep learning. Some of the limitations are this: it just does not understand word order or deep meaning. Can struggle with very advanced phishing emails. Now let's move on to technique two: support vector machines, also known as SVM. Sorry, SVM creates an optimal boundary between spam and ham in a high dimensional space. The strengths of these is that it's often very high accuracy and good precision, and works well with text feature spaces like TF-IDF. Some of the limitations requires more tuning and pre-processing. Training can be slower than naive Bayes, less interpretable, and so on. Now, technique three, CNN. CNNs can also work for text classification by detecting patterns like phrases or local word sequences. Some of the strengths: learn features automatically, strong against obfuscation and more complex spam styles. Some of the limitations of CNNs is that it requires very, very large data sets and needs much more power and stronger GPUs to compute, and it's hard to interpret. Now we go on to part C, where we look at my implementation in the notebook. Now we can actually explain my prototype. So we move on to dataset description. I use a dataset called emails.csv from Kaggle. It contains 5,728 emails with two main columns, um, text and spam. The email content there was labeled where 1 equals spam, 0 equals not spam. I first inspected the dataset using a df.info and confirmed that there were no missing values in these columns. Um, exploratory data analysis before training. I did some uh, EDA, class distribution plot. This shows how many spam and non-spam emails exist. This matters because if the data set is highly imbalanced, accuracy alone can be a bit misleading. Two, email length distribution. I created an email underscore length feature, plotted it by class. In many cases, spam emails can show different lengths and patterns compared to ham. The word cloud for spam emails. This visually shows common spam words such as free, money, click, account, and similar promotional language. Um, One thing I found out is the top frequent words in spam. I use counter vectorizer, which is often included in web marketing signals like HTTP, com, business, free, and email. This EDA supports the idea that spam emails have strong repetitive vocabulary patterns, which is why naive Bayes can perform very well. Um, Text pre-processing functions. Um, then I built pre-processing functions to make the pipeline reusable for prediction. My pre-processing steps will remove the subject prefix, convert to lowercase, and remove URLs, remove email addresses, remove numbers, remove punctuation, normalize extra spaces. This produces a clean, consistent string that is better for vectorization and model learning. Moving on, then I applied pre-processing to the dataset and created a new column called clean underscore text. Then I did a train slash test split. After pre-processing, I performed a stratified train test split. 80% training, 20% testing, stratification, and keep spam and ham ratio similar in both sets. Yeah, and like that's really important for good and fair evaluation. When looking at proper machine learning pipeline, I built a scikit-learn pipeline, which includes count vectorizer, stop underscore word equals English, ngram underscore range equals 1, 2. So it uses unigrams and bigrams. Min underscore df equals 2 to ignore extremely rare words. Multi-novel naive Bayes alpha equals 1.0 for Laplace smoothing. The key advantage of a pipeline is that it ensures the same features and extraction and model behavior happens consistently during training and during prediction. When we look at part D, testing, evaluation, and results, um, uh, when we look at that testing methodology, my main testing approach was a train test split for unbiased evaluation. Data integrity checks for things like empty strings after cleaning reproducible at random state. We look at uh, expected versus actual performance. Before training, I expected around 90 to 95% accuracy because naive Bayes usually performs strongly on text spam data. But after evaluation, my actual accuracy was around 98.95%, which is much higher than expected. This suggests that in this data set, spam and ham have very clear vocabulary differences. But I also mentioned academically that this may not fully represent real world spam complexity, obviously, especially in advanced phishing and so on. Now let's look at performance metrics and what they mean. Uh, Accuracy overall correct, and predictions, classification report, precision, recall, and F1 score for each class in spam detection. False positives mean real emails incorrectly sent to spam. False negatives mean spam emails missed and delivered to inbox. So precision and recall matters a lot. When we look at what's in my result, uh, I added a few visual evaluation plots. I also included multiple evaluation plots such as confusion matrix, heat maps. This shows counts of incorrect and incorrect classification. My model had very few errors, only a small number of false and positive and false negatives. I did ROC curve and AOC. I computed predicted probabilities and plotted the ROC curve. The AUC was around 0.998, which indicates excellent class separability. Number three, precision recall F1 bar chart. This visually compares metric scores between spam and ham, showing balanced performance. Predicted spam probability distribution. This histogram showed many predictions close to 0 or 1, which means the model is usually confident rather than uncertain. We talk about misclassified email analysis. I printed misclassified examples. There were only about 12 misclassified emails, which is quite small. These are usually borderline messages that contain overlapping language patterns. Now we go up to prototype and inference functions. Next, I built a function called predict underscore email. This function takes a raw and email text and returns clean text. Prediction label spam or not spam, probability of spam and not spam. I tested it with 2 sample emails. For congratulations, you won $1,000. Click here, predict the spam. Meeting tomorrow at 10 a.m. predicted not spam. This demonstrates how the system works like a real filter. Part E, EDI and sustainability. Finally, I discuss EDI and sustainability. EDI, fairness and inclusion. Even spam detection can have fairness issues. If training data mainly represents one writing style, like formal English, then the model might wrongly flag informal English, mixed language emails, different cultural writings, styles. This may cause unfair false positives. So a few improvements could include testing on diverse datasets, user feedback features like mark as not spam, providing simple explanation for decisions, In terms of sustainability, deep learning spam filters can use a lot of compute and energy, but naive Bayes is lightweight and CPU friendly, so it's more sustainable and low cost for many smaller organizations. A model like this is a good balance between performance and resource use. Now, conclusion. To conclude, I built an AI-based spam detection system prototype using strong pre-processing and a clean pipeline design, multi-nominal naive Bayes, detailed evaluation metrics and plots. This system achieved very high performance on the dataset and the pipeline, supports real-time prediction on raw emails. In future work, this could be extended using TF-IDF and SVM comparisons, deep learning models like CNNs, metadata features like sender reputation, continuous retraining to handle spam evolution, retraining to handle spam evolution. Well, that is all of my applied AI coursework. Hope you enjoyed and thank you for watching.